computer is really uncomfortable. I wish there was a better way, but even these stands suck.
Have you heard of SmartStand? It's a computer stand that automatically adjusts to the ideal ergonomic position for any user. It also implements eye strain and stretch reminders to improve user health.
Whoa, let's check it out.
All you have to do is plug in the power, then you start the application, and then you can put the computer on the stand at an arbitrary angle. And now you have to calibrate your setup by lifting the computer so SmartStand knows what to look for when adjusting the stand. Now that calibration is complete, SmartStand will automatically adjust. At this point, SmartStand has found the ideal angle and height, so a user can just use a keyboard and work away in a very ergonomic setting. Mechanically, SmartStand consists of a platform jack and an upper layer with linear actuators. To drive the platform jack, we have a high torque stepper motor, which rotates a lead screw that is connected to the stepper motor with a coupler. And then to change the angle of the computer, we have two linear actuators. We opted for a platform jack because it's very compressed at its closed state, but you can still has a very large range of motion. SmartStand also has a built-in posture detector, which will give you a friendly reminder if your posture is not as good as it could be. The way it works is you initialize and calibrate the model by pressing C on your keyboard, which captures a reference. And then once your posture starts to deviate slightly from what it could be, you get a little reminder to please correct your posture. And then once you do correct your posture, notifications stop. The way that the posture detector works is it uses landmarks between your shoulders and on your nose and uses the distances between those landmarks.
The overall block diagram for our system is shown here. As you can see, our system uses the camera to pass visuals to OpenCV, which will then be used to determine the user's posture, position, and focus. This data will then be passed through our code, which will 1. Use an algorithm to alter the position of the stand when prompted, 2. Determine if the user has bad posture, if so, a notification will be sent to the user for feedback, and 3. Determine if it is time for the user to receive notifications to look away from the screen or to stretch. These notifications will be visible to the user in the GUI. On the user's end, they will be able to enter calibration settings, including automatic and manual adjustment. The software will communicate to the stand's hardware via Bluetooth, specifically an ESP32 module that is installed within the Arduino. Depending on the input that is received from the laptop, the stand will adjust in height and angle. Here, the communication between the software and the hardware is shown in more detail. Each of these signals is configured as a characteristic of the Bluetooth service running on the Arduino. When the reset signal is received, the stand will revert back to the start state and initiate a turn-off function that will revert the stand to the initial height and angle. The start signal is used to transition from the start state to the adjust state, and when this signal is received from any other state, it will simply return the Arduino to the start state. This system was needed to ensure that the user can continue to make adjustments to the stand with the app running without the stand turning off. Then, once in the adjust state, the stand can receive a height or angle signal. When the height signal is written to 0, the stand will lower, and when it is written to 1, the stand will raise. This is the same for the angle signal. Once the user is finished adjusting the stand, or the stand has been confirmed to be in the ideal ergonomic position, the done signal will be sent to the stand, which will then cause it to enter the done state where no further changes can be made to position. After each of these transactions, an acknowledgement signal will be sent back to the laptop to let the software side know that the signal was received and that it can continue sending messages. If no acknowledgement signal is received, the transmission will time out and attempt to resend.
In order to determine the ergonomic height and angle at which to adjust a user's laptop to, we used OpenCV and dlib68 landmarks to track the user's facial positions. So using dlib, we detected a user's face using their live camera feed from their laptop and tracked the coordinates of the user's facial landmarks. So during calibration, we asked the user to angle their face flush to the screen, and then we record the landmark positions of their face at this stage into a file for record keeping. So using these landmarks as reference, we can later adjust the laptop without asking the user to recalibrate. And then during the adjustment process, we use an algorithm that calculates the horizontal landmark distances between a user's eyes and the vertical landmark distance between the midpoint of their eyes and the tip of their nose. So as you can see, the vertical landmark distance changes when the camera is angled up, down, or directly in front of a user's face. This is also true for horizontal landmark distances, and using these two distances we can create a ratio in order to determine whether the laptop needs to increase or decrease height or angle. We use a ratio of these distances so that a user can be any distance away from the camera and still get an accurate adjustment process. So to do this adjustment, we first adjust the height of the screen until the user's eye line is at the midpoint of the screen, and then we adjust the angle of the screen until the ratio of landmark distances is within a threshold of the ratio that we calculated at calibration. So we then iterate through these two stages until both of these conditions are true. Similarly, to track a user's focus and whether they've been looking at their screen for long periods of time, we use variations in the vertical and horizontal landmark distances. Here we use different landmarks for the side of their face and the same one for vertical landmark distances. So we can use these to detect whether a user is looking up, down, to the side, or straight at their screen. So from this information, we can record how long a user has been focusing straight at their screen, and then use notifications to remind them to periodically take breaks for their eyes to unfocus in order to prevent eye strain. And then for stretch reminders, we use dlib's face detector just to detect whether a face is present in the camera feed, and then when a user's face is detected, that would signify that they're sitting in front of the screen, and if this is detected for long periods of time, then we remind them to get up to take a stretch break. First open up, you can see there's stand controls and tracker views. So first take a look at the trackers. Here you can have a tracker that will notify you when your posture is bad, such as hunching or slouching. You can also start a focus detector, which will track whether you've been looking at your screen for long periods of time and remind you to take a break for your eyes. And then also a stretch reminder, which will remind you to get up and go stretch every once in a while. And this is what the notification will look like if you've been looking at your screen for long periods of time. So here we can go to stand controls, and here you have options for ergonomic auto adjustment or manual adjustment. In manual adjustment, you can just use these button presses to increase your angle or decrease your angle for the laptop stand, or adjust the height up or down. Additionally, you can reset back to the lowest height and lowest angle setting. We can also go through the ergonomic auto adjustment, which will be the automated adjustment process that will determine whether the stand needs to raise or angle. So in the auto adjustment, you first have to calibrate your setup. So here it'll give us some instructions to angle our face towards the screen, and then type E to calibrate. Here it'll just gather my landmarks and save that. Then we can go back and start the automated adjustment.